I welcome you all to my video lecture presentation. I am C. Ashok Kumar, Professor, Department of EEE, and my course name is Electronic Device and Circuits, and the topic name for today's lecture is Comparison of Rectifiers and Problems, which comes under the Unit 2, Diode Applications. Okay, the overview of my presentation goes on like this. First, I will be comparing the rectifiers, all the rectifiers, half-wave rectifier, full-wave rectifier and bridge rectifier with respect to the parameters of rectifiers. And then some problems I will be doing related to half-wave rectifier as well as the full-wave rectifier. And finally, I will be recapping the things whatever I discuss. So, the first topic is these are the textbooks here. Electronic Device and Circuits by Jacob Millman, and second textbook is Electronic Device and Circuit Theory by Bollisted, and third one is Electronic Device and Circuits by Salivahanan. And the first topic is the comparison of rectifiers. As already we discussed about different types of rectifiers. The first type is the half-wave rectifier, and second one is the full-wave rectifier, where you will be making use of a center tap transformer. And the third one is, it also comes under full wave rectifier, but it is an improved version of the full wave rectifier, that is called as a bridge rectifier. Okay, and these are the output waveforms. As you can see, half wave rectifier, and this is output waveform for full wave rectifier, and same thing happens here in the bridge rectifier. Okay, whenever you are giving the AC input voltage. AC input voltage means it is a sinusoidal signal which consists of both positive half cycle and negative half cycle. Okay, so now let us go for the comparison. So here I am taking the parameters, as you can see here in this particular column. How many diodes are there in that particular rectifier? That is a parameter 1, and parameter 2 is output frequency. Output frequency in the sense, whenever you are providing the AC input voltage, it has got some frequency. It may be 50 Hz or 60 Hz. Okay, 220 volts or 230 volts AC. AC means it has got some frequency, that is 50 Hz or 60 Hz. So output frequency. What happens to the output frequency if it is half wave, if it is a full wave, if it is a bridge rectifier? Let us see. And third parameter is DC load current. DC load current, that means average current value, already we derived. And next one is DC voltage, no load DC voltage, that is VDC. Okay, and next one is about IRMS values. IRMS value, root mean square load current value, and here RMS value, VRMS value, and that is one more parameter. And next one is about the efficiency. Efficiency in the sense it is a rectification efficiency. And the next is TUF parameter. TUF parameter, transformer utilization factor. And next parameter is the ripple factor, which is a main important parameter of all the remaining parameters, which is called as a ripple factor, which judges the performance of any rectifier. Okay, next is the peak inverse voltage, that is represented as PIV, and next is the ripple frequency. Okay, so these are all the parameters by which I am comparing the rectifiers. First one is the half wave rectifier, second one is the full wave rectifier, and third one is a bridge rectifier. Okay, so how many diodes are there in the half wave rectifier? Only one diode will be using, that's why 1. If it is a full wave rectifier where we are making use of a center tap transformer, the number of diodes we use are, as you can see, 2 diodes. Okay, and if it is a bridge rectifier, as you can see, 4 diodes will be using. And what about output frequency? Output frequency means whenever input frequency is Fi, the half wave rectifier, the frequency of output will be remain same as input frequency. And if it is a full wave rectifier, the output frequency will be 2 into input signal frequency, 2 Fi. And here also same thing happens in bridge rectifier. Frequency means, as I already said, it may be 50 Hz or 60 Hz. Okay, so next is IDC value. If it is half wave rectifier, IDC value will be Im by pi, where Im is the peak value of the current, and if it is a center tapped full wave rectifier, the value will be 2 Im by pi. Same thing will be there in the bridge rectifier also. Why? Because bridge rectifier comes under the category of full wave rectifier. Okay. Next, the current, the DC current, that is nothing but simply replacing the current with voltage. We can see here Vm by pi, and here it will be 2 Vm by pi, and here it will be 2 Vm by pi. Okay. Next, RMS values. RMS values of both current and voltage. So here, if it is a half wave rectifier, it will be Im by 2, and if it is a center tapped full wave transformer rectifier, it will be equal to Im by root 2. And same thing is valid for bridge rectifier also, that is equal to Im by root 2, where Im is a peak current value. Okay. Next, RMS voltage. RMS voltage means Vm by 2 here, half wave rectifier, and full wave rectifier center tapped is Vm by root 2, and a bridge rectifier it will be equal to Vm by root 2. Once again same value. And here efficiency, rectification efficiency, if you calculate the value of half wave rectifier is 40.6, and if you calculate the rectification efficiency of full wave rectifier, that is center tapped full wave rectifier, the value will be equal to 81.2%. If we talk with respect to percentage, the value will be 81.2%. And next one is bridge rectifier. Same value is valid here. Okay. Next, this TUF, transformer utilization factor. As you can see here, a half wave rectifier, one value will be defined, and center tapped full wave rectifier, it will be around 0.8, and if it is a bridge rectifier, it will be reduced. Okay. So this is also one parameter. Okay. Next, ripple factor. Ripple factor means if we go for the half wave rectifier, the value will be equal to 1.21. So 1.21 means, as you can see here, ripple value is represented by gamma. So here VAC by VDC. So VAC by VDC is equal to 1.21 means it is greater than 1. So VAC by VDC is greater than 1. That means VAC is greater than VDC. Okay. So if you observe the rectified output of half wave rectifier, as you can see by this relation, the AC components are more when compared with the DC components in the rectified output of half wave rectifier. So that is poorer performance for half wave rectifier. That's why we will be going for full wave rectifier. What is the ripple factor of full wave rectifier? It is 0.482. That is less than 1. Less than 1 means what is the meaning here? VAC is less than VDC. That means DC components are more contained in rectified output of full wave rectifier. Okay. So that's why the performance is good here in this case of full wave rectifier when compared with the half wave rectifier. So same value is valid for bridge rectifier. So peak inverse voltage, it will be equal to Vm. Peak inverse voltage means the maximum value that is withstanded by the diode in the reverse bias. Okay. So that is Vm if it is a half wave rectifier, and here the value will be equal to 2 Vm, where Vm is a peak value of the provided input voltage. As you can see, this is Vi, AC signal. So this is Vm, peak value. Okay. So here 2 Vm, and here if you go for the bridge rectifier, so here 2 Vm is being shared by 2 diodes, I said already in the last class. So you will be getting Vm here, Vm per diode. So 2 Vm per diode here in the case of center tapped full wave transformer. It is reduced here. Okay. Next, ripple frequency, here Fs, here 2 Fs, and here 2 Fs. So this is about the comparison. The comparison means we need to take some parameters and we need to compare with the different rectifiers. What are the different rectifiers? So first one is a basic type half wave rectifier, and second one is a center tapped full wave rectifier, and third one is a bridge rectifier, comes under the full wave rectifier. Okay, this is about the comparison of rectifiers. And next, let us go for the problems here. So the problem comes under the half wave rectifier. Okay, the problem is a half wave rectifier having a resistive load of 1000 ohms. Okay, rectifiers an alternating voltage of 325 volts peak value. Okay, and a diode has the forward resistance of 100 ohms. Okay, this is the given data. He is asking to calculate. First one is, sub question is, calculate the peak value of current and average value of current and RMS value of current. Okay. Second question is, calculate the DC power output. And third question is, calculate AC input power. And fourth one is, calculate the efficiency of rectifier. Okay. Let us calculate one by one here. So what is the first one here? Calculate the peak value. So peak value means, as I already said, so this is, the signal is represented like this, whether it may be a voltage waveform or current waveform. So here I am taking it as a voltage waveform. So this value is called as the peak value. Similarly, if it is a current signal waveform, so I am writing it as II. So here the peak value means, here it is represented as IM. Okay. So he is asking to calculate the peak value of current. So what is the provided data here? Load is given. So load is given. So load means we will be representing the load as, so if you draw the circuit diagram, let me draw the circuit diagram roughly here. So this is a load resistance RL. Okay. So here input is provided Vin and output will be absorbed across the load resistance RL, and this is a diode. Okay. So peak value of current. Peak value of current IM. So IM is equal to VM by RL. But here, along with load resistance, the forward resistance of the diode is also provided here. As you can see here, forward resistance of the diode is given as 100 ohms. That means RF is equal to 100 ohms. And load resistance value, that means it is capital RL. This means this one. Load resistance value is given as 100 ohms. Sorry, 1000 ohms. Okay. So RF is given, RL is given. And what is the peak value of voltage? Input voltage 325 volts. That means VM. VM is equal to 325 volts. Okay. These are provided data by the problem here. Okay. So IM is equal to VM by RF plus RL. So VM is 325 and RF is a forward resistance, that is 100 ohms, and RL is a load resistance, that is 1000 ohms. Okay. If you go for the calculation, you will be getting the IM value as 295.45 milliamperes. So next, average value of current. Average value of current for full wave rectifier, what is the formula? IDC is equal to IM by pi. You know the value of IM as 295.45 milliamperes by pi. If you go for the calculation, you will be getting IDC as 94.046 milliamperes. Okay. Next, RMS value of current. IRMS of half wave rectifier is IM by 2. Okay. IDC value is IM by pi and IRMS value is IM by 2. So IM value already we got it as 295.45 milliamperes by 2, and you will be getting 147.725 milliamperes, right? So next, second question, calculate the DC power output. That means PDC. DC power output means PDC, the formula is equal to IDC square into load resistance RL. So IDC already you got the value as 94.046 milliamperes, means into 10 to the power of minus 3 whole square into RL. RL value is 1000 ohms. Okay. So you will be getting 8.845 watts. Okay. PDC is equal to 8.845 watts. Next, AC input power. AC input power means here. So what is the AC input power here? IRMS square into we need to consider the forward resistance of the diode as well as the load resistance here, because it is input power. If it is output power, we need to consider only RL. Output is taken across the load resistance RL. But here input power means we need to consider the diode resistance also, forward resistance. That's why here the formula goes on like this: IRMS square into RF plus RL, where RF is the forward resistance of the diode. So IRMS value already you got it as 147.725 milliamperes into 10 to the power of minus 3 whole square into RF plus RL. RF is 100 ohms and RL is 1000 ohms. So you will be getting 1100. So if you go for the calculation, you will be getting 24 watts. Okay. So next final question: efficiency of rectifier. Efficiency, the formula is rectifier efficiency eta is equal to PDC by PAC. So PDC you got it as 8.845 and PAC is 24. You will be getting 36.85. Okay. So this is about the problem related with the half wave rectifier. So next problem which comes under the full wave rectifier. Okay, let us study this particular problem. So determine the DC output voltage, peak inverse voltage and the rectification efficiency for the circuit shown in the figure. So these are circuit provided. Circuit already in the data itself, the circuit is provided. It is a center tapped full wave rectifier. As you can see, 2 diodes and load resistance RL. Okay. So input voltage is 230 volts, 50 H AC supply. Okay. So here the data given here by this particular circuit diagram is RL value is given and this turns ratio is given. Turns ratio means these are primary and these are secondary winding. The number of turns of primary winding, let it be N1, and the number of turns in the secondary winding, let it be N2. Okay. And let the voltage provided here input is V1. And what will be the output voltage here across the secondary of the transformer based on this number of turns ratio? If it is a step down transformer, kindly remember the number of turns of the secondary windings will be less. If it is a step up, the number of turns of the secondary will be more. But here it is 5:1. That means N2 is equal to 1 and N1 is equal to 5. That means it comes under the category of step down. Okay. So what is the value of V2 here? So this is a V1 provided input voltage to the primary of the transformer. And what is the output voltage V2 here? So if you go back to the basics, we can write this equation. V2 is equal to N2 by N1 into V1. That is the formula. Okay. N2 is the number of turns of secondary of the transformer and N1 is the number of turns of the primary winding of the transformer. Okay. So this is a formula. We need to make use of this formula in this particular problem. First, what is the DC output voltage? First question is, what is the DC output voltage? So what is the DC output voltage? That means we need to obtain the value of VDC. As you can see here, VDC is equal to IDC into RL. So first you need to calculate the value of IDC here. So how to calculate here based on the given data? So it is a center tapped here, center tap transformer. Center tapped means here V2 will be divided into 2 halves. So upper portion is V2 by 2 and lower portion is V2 by 2. It is a center tap, not a conventional transformer. So if you apply this particular formula, V2 output voltage at the center, at the secondary of the transformer, which is a RMS value. So V2 is equal to N2 by N1 into V1. So what is N2 here? N2, 1. Number of terms of the secondary. 1 by N1 value is 5. 1 by 5 into V1 provided value is 230. Okay. So here this is a V2 value across the secondary, but it is a center tap. It is a center tap transformer. So this V2 has to divided into 2 halves. That's why here simply I am making it as 1 by 2. So 230 by 10. 230 by 10. As you can see here, you will be getting 23 volts. So that is the VRMS across the secondary of center tap transformer. So what is the value? We got 23 volts. So by this formula 230 by 5, because it is center tap, we need to divide it into 2 parts. That's why I am dividing with 2. So you will be getting 23 volts. That is a VRMS value across the secondary of center tap transformer. Okay. So what is the relation between VRMS and peak value? VRMS is equal to Vm by root 2. VRMS is equal to Vm by root 2. This is a relation we got in the full wave rectifier. VRMS is equal to Vm by root 2, where Vm is a peak value and VRMS is a root mean square value. So what is the value? What is the value of Vm here? Vm is equal to root 2 into VRMS. Okay. So same thing here. So Vm is equal to root 2 into VRMS. So VRMS already we got it as 23 volts. So you will be getting Vm as 32.53 volts. Okay. So next Im. So Im is equal to Vm by RL. Okay. Vm by RL. But here the formula he wrote it as Vm by RL plus RS plus RF. RL means, this is RL, okay, load resistor, and RS is the resistance related with the secondary of the transformer, and RF is the diode resistance. But in the given data, RF value and RS value they did not provide. So that's why here we can ignore these two values. One is RS and other one is RF. So directly we can write it as Vm by RL. So Vm value is 32.53 volts by RL means 100 ohms. So we'll be getting 0.3253 amperes. Okay, that is the value of Im. So from Im, we need the value of IDC. So IDC is equal to, what is the relation between Im and IDC? For full wave rectifier means IDC is equal to 2 Im by pi. So Im value we got it as 0.3253 by pi. You will be getting 0.2071. That is the value of IDC. But what is the question here? You need to obtain the DC output voltage. So DC output voltage VDC can be written as IDC into RL. IDC value we got it as 0.2071 and RL value already given data, that is 100 ohms. So 0.2071 into 100, you will be getting 20.71. Okay. So next question is, he is asking the peak inverse voltage. Already you know that the peak inverse voltage of full wave rectifier, center tapped full wave rectifier is 2 Vm. If it is a bridge rectifier, the value will be Vm. And if it is a center tapped full wave rectifier, the value will be 2 Vm. Okay. So PIV is equal to 2 Vm. Vm already we got the value of Vm. What is the value of Vm here? 32.53. So 32.53 into 2 will be getting 65.06. So next, last sub question, that is the rectification efficiency. You know the formula of rectification efficiency. The formula is PDC by PAC. DC output power by AC input power. So PDC formula is equal to IDC square into RL, and PAC formula will be equal to IRMS square into RL. Why? Because RF and RS value are not given. So by making those values, so you'll be getting, so here VRMS value is 23 volts, IRMS value means 23 amperes. Okay. So like that, if you calculate PDC and PAC, PDC is IDC, PDC means IDC square into RL, and PAC means IRMS square into RL. Okay. So if you go for the calculation, you will be getting 81.07. Okay. So this is a problem related with the full wave rectifier. So let me recap the things whatever I discussed. First, we discussed about the comparison of rectifiers with respect to so many parameters. Comparison of rectifiers. What are the rectifiers? One is a half wave rectifier. Second one is the full wave rectifier, the center tapped full wave rectifier, and third one is bridge type full wave rectifier. We compared the three rectifier with respect to so many parameters like ripple factor, rectifier efficiency, transformer utilization factor, and so on. Okay, and next we have done some problems related with the half wave rectifier and full wave rectifier. Okay, so with this I conclude the discussion related with the rectifiers. In the next coming class, I will be saying about the filters. Why you go for filters? What is the need of going for filters? That will be discussed. Okay, thank you.